given by so it's a scalar field theory in the dimensions in Euclidean space, and I'm coupling the field to this field H, which is a disordered field. It could be a random field in our model, and we will take this H field from this probability distribution, where P is a normalization constant, sigma is some kind of standard deviation, so this is the model that we will be studying. I will start pointing out a few differences with respect to the model which you saw last lecture, which is the following. This model is a continuous model, and last lecture we saw a model in the lattice. This model actually is the continuum limits of the Eisen model in the dimensions, but with homogeneous coupling, so no random coupling. So now the disorder is not in the couplings of the theory. The disorder now is in an external field, so it's kind of different from what we saw in class. Okay, so we want to study this theory with disorder, and when you have this kind of disorder in a system, it's hard to study the field theory because of the following reasons. First, the correlation functions of the theory start to depend. They are not translation invariants anymore. Like the propagator is not a function of the distance of the points because you have some local dependence via this H field, which is non-homogeneous in general, and it's hard to make some perturbative calculations. Also, because of this H field, if you study the saddle point equation for the defining like classical minima for the theory, you end up with an equation like this. And then, just like last lecture, we expect that the field will have lots of local minima, possible local meta-equilibrium states, and then it's kind of weird to do a perturbative expansion because you need to choose a vacuum, but you have so many local minima that it can be hard to choose one. So what we'll do to circumvent this problem, the absence of translation invariance and so on, we will average over the disorder just like we did last lecture. And to do this, we want to do a quantitative average just like last lecture because we want to imagine that the disorder coming from this H field is static. It's not a dynamical disorder that is changing over time, it's a static disorder, so we have to do a quantitative calculation of some kind of extensible observable like the free energy. So we will average the log of this partition function instead of the partition function itself. And last lecture we saw a way to do this calculation via the replica method, which would use this identity to make the calculation. But in this paper, the authors use a different method to obtain the quantitative average free energy, which is not a replica method, which they call the functional distributional zeta function method. And I will not go over the steps that they go through to explain how they do this, but the idea, the final result is that you can express this average like this with their method. where this A constant that I wrote down is just an arbitrary real number in which the quantity of free energy does not depend on something. So this does not depend on A. A is just an arbitrary real number here. This is just the average, but without the log. It's the average of the kth power of the partition function. So you have to sum from 1 to infinity of powers of the average value of the partition function, and you have these residual terms. These are, I think it's the other constants. This is the log of A, and this R, it can depend on the parameters of the theory, but it respects this inequality right here. Sorry. Zero. Okay, so the idea is that since this expression, the free energy, does not depend on A, what we will do to get rid of this contribution from this R function, which we do not know how to estimate, is, well, we know that it respects this inequality right here, and Z is positive definite. So if you take a very large value for A, we will be able to ignore this contribution right here. We will do it we'll do it soon. But okay, so this is our representation for the quantity free energy, which is not using the replica method, it's this distribution that the function method. So to proceed to calculate the free energy, we need to obtain these guys right here. So I will write, just to make it explicit. Where I write the table like this, just to be quicker. But yes, you do the k power of the partition function, you just have k replica fields defining the k power of the partition function. So we have one copy for each k. And now we want to calculate the average with respect to the probability distribution for the H field. This will be a regular path integral, which we can do because H only appears quadratic, in a quadratical way, inside the probability distribution, and linearly coupled to the H field. So we can do some completing the square, and after completing the square and doing the path integral over, and doing the path integral over H, we end up with this theory. Where the effective action after integrating out the H field, which is the disorder, is this. Sum. Where this Okay, so what happens when you integrate out the H field is that all the fields get like an extra mass term of sigma, but not only between like a regular diagonal mass term, but all with themselves when you complete the square, because you get some sum over FI squared. Okay, so we have this expression, and for each zk, this is after you do the integration over the issue. So with this, we can ask, what is can you get a saddle point estimation for FQ using this expression? So what we will do is to evaluate each zk at the saddle point. So let's write down the saddle point equation to the field, which will be very similar to this equation right here. So what I'm saying is this: let's extremize the effective action with respect to one of the replica fields. When you do this, we'll get k equal equations because they have replica fields have permutation symmetry. All the equations will be equal. And you get this when you do the saddle point calculation for direction. And now what the authors do is the following. So let's study a replica symmetric ansatz, in contrast to what Parisi did in his paper. And by replica symmetric ansatz, they mean assuming that all the fields are equal in each replica partition function zk. So if you assume that all the fields are equal, so this we can write as just k times phi. And then now what we can do is put this in the other side. So I'll just rewrite this really quickly. Okay, so now something really interesting happens, which is the spontaneous symmetry breaking in the title, which is the following. So let's take m0 to be a positive value, and now let's look at the integer part of this number. So we see that if k is smaller or equal, let's call this kc, critical k. If k is smaller or equal to this value, what happens is that m0 squared will be bigger than k sigma. And in this case, then, we have like an effective positive mass, and there's no spontaneous symmetry breaking because the zero will be an classical stable equilibrium point. However, for values of k that are bigger than kc, then this will be bigger than m0 squared, and then this will become negative, so the origin will be an unstable classical equilibrium point. So now we have spontaneous symmetry breaking in these scenarios. So the idea here is that we have a series of replica partition functions for each value of k, and then some of them will have spontaneous symmetry breaking, some of them will not have spontaneous symmetry breaking. So, okay. So in Parisi method, there is explicit replica symmetry breaking via the ansatz, and the free energy. Here we start with an imposing replica symmetry, and we get spontaneous symmetry breaking of this Z2 symmetry for these fields. And because of that, the authors also call this phenomenon replica symmetry breaking. It's not the same that happens in Parisi, but they call it replica symmetry breaking because inside each of these terms, zk of the series, inside each of them, all replica fields are the same. But if you go from one replica partition function to the other, they will have different vacuum expectation values because this k will be different for each one of them. So we will get, like, we have replica partition functions which have different fields inside them, but inside them all the fields are equal. So they also call this replica symmetry breaking. Okay, so with this notion of replica symmetry breaking, they propose an ansatz for the whole structure of the replica fields, which I will write right now. So they propose that you take n bigger than kc to define this n, and you do the following. This upper index right here will index which k from which partition function we are talking about, from which partition function these fields are from. So we'll take this to be a regular function, a regular field, when L is smaller than smaller or equal to than Kc, and E goes to 1 all the way to L, in this case, so we have L replicas. Okay, so what should we do is where also let me define V. Okay, this is V. Okay, so for the fields in which don't have spontaneous symmetry breaking, we just keep them as regular field variables. The ones that experience spontaneous symmetry break, we shift by V, but now V is the back expectation value when k equals n. So even for L smaller than n, we still shift by the back expectation value of k equal n. So to be honest, I didn't really understand why they make the answers like this, and then they don't shift by a v of k in which n is replaced by k. But this won't matter in what I will discuss in the following. And then for L bigger than n, we just set all the fields to 0. So it's like truncating the series at k equal n, what they are doing here. And then we should take, after this, the large n limit to obtain the equation-free energy. Okay? And after they do this, we can then Okay, we can then evaluate the equation-free energy in the truncated version, and then take the n goes to infinity limits. So when we do this, we will take the A constant that I said earlier to very, very big value, so that we can suppress this R contribution, which we don't know how to calculate, but we know that if we take very large values of A, it should become as small as we wish. And then in the truncated series, since we have A to the K here, and A will be very big, we can just keep the last term of the series, which is K equal to N in these limits. And then we approximate the equation-free energy. It's like a saddle point approximation. Just get the biggest contribution, which would be of the order of Z to the N. And then to get the actual equation-free energy, we take the large N limits. So the result is the following. We can write the partition function of this model, the free energy of this model, as a replica field theory of n fields, and then we just take the large n limits of this theory. And then they comment about a curious result, which is the following. We derive this for any dimension, any value of d. And however, to get for d, for dimension bigger than 6, it is known from renormalization group argument that the ON model, the large n limits of the ON model is not useful to describe the critical points of the ON theory in dimensions higher than 6. However, we obtain independent of the dimension that to obtain the free energy of this disorganized model, we have to work in some kind of large limit. And then, thus, in some way, the large n expansion is a useful expansion for d higher than 6 when we have disorder. So there is some kind of non-trivial connection between disorder and the large n expansion. So this is a comment that they make, and I think. Sorry, I didn't get which time I started.
No, you should. You are beyond time.
Okay, so that's it, and thank you.
Thank you. Yeah, this paper looks wrong to me. I think I'm surprised. Yeah, there are so many things that look wrong. I mean, I did not read the paper, but it just seems wrong. Is this method accepted, and do other people work, or is it something they come up with?
You mean
There are so many things that are suspicious to me.
You mean this representation of the free energy using the distribution of data?
For example, this representation is not manifestly extensive. You have a sum of terms. Each z is exponentially small. Why is this an extensive quantity? Why is this proportional to the volume? How can we estimate the large asymptotics of a series by truncating the series? That's exactly what we cannot do.
I agree with that. Maybe I didn't understand very well what they are doing here, but they do this truncated ansatz and evaluated it at large n. But I also a bit suspicious of this truncate and take the large n limits. And I don't have an answer for this.
Z is exponentially small.
Yes.
It's really tiny. So A needs to be huge, like size of the universe. And then you are going to say A is huge, now truncate the series at 20 terms and take the term number 20. Alright. Are you on drugs? I don't know, this paper is wrong. I'm still proven otherwise. Is this a very well cited paper?
I think when I saw it was about.
We should remove the video.
Oh, it's about I think 17 citations from 2017.
Okay. I'm very skeptical about all this. Maybe you could tell me. Is this a method that people say, oh, one representation of log z is the trick we saw, there's another representation of log that uses some gamma functions, and that leads to this other representation, and people also use it for spin glass. Maybe I could stop being convinced if you tell me
this representation.
Other people use it in other contexts, but right now,
so I didn't.
It just looks.
Yeah, I didn't look for other papers that use this representation. I know that this representation was developed by one of the authors of the paper in a previous paper, and they also have a review here. They explain a little bit about this representation. It uses some measure theory, and I didn't understand it quite well because I haven't studied this kind of math. But it's derived using some measure theory in page 3.
For example, they have a paper that cites this paper, which is the SK model via the SK model, which is what we did in class, via the distributional zeta function method. So if that paper manages to match the results of Paris in some way and explain the connection, I could start believing, but this just looks Then, as you say, there is a k that becomes an n. There is what is this n? Now n is large, but then there was no n. N is totally ad hoc, right? There's no n in the model. Then you say it's
hey, the n is the number of replicas which comes from this summation.
yeah, but then the free energy is going to be e to the capital N times something, right?
Sorry?
The free energy is going to be given by settle point. So the settle point of z to the capital N gives exponential something.
Yes.
It's totally wrong. The free energy is not exponential something. It's linear. In the volume, it's why are these exponentials?
Well, after the actual carry for dimension smaller than 6, or for equal 4, in which you don't expect a good description via settle points, they do one loop calculation of a few things in the large n limit. And so the way they take the large n limit, actually they maintain this fix. Take n to very large, but then you have to take the disorder to be very small as a consequence to maintain this parameter finite. And
sorry, f is z to the n. Z to the n is an exponential quantity. So f is an exponential quantity. That's
yes.
all.
No, but n is not. No, yeah, but n is not an extensive quantity of this of the regular theory. It's just this.
Whatever, even if n is finite. If the approximation is take one term of
Yes.
and say that f is z to some power, whatever power it is, that's an exponential quantity. F is not exponential. It's wrong. Yeah. Connor, do you agree?
Yeah.
Yeah.
Yes.
Well, maybe we'll be sued by the authors, we'll see the video online, but it's still an important lesson that there are papers in the archive that are wrong. This exists. It's something we should be aware.
You said that the needs to be large, right? For this, is it obvious that first series converges at all? It's going with power that's ridiculously large. Did they justify this somehow?
Well, they derive this as a representation of expectation value of log z. So if this representation is correct, I think it should converge. But I didn't go into details of this, the derivation of this representation, I just used it.
Very good. Okay, let's thank Marvin. Now I'm curious. If you would have a look at, I would have a look at the paper where they apply it to the SK model. That's a model that's very well studied, right? The energy of the ground state is 0.76. Yes. If they can get 0.76 with this Macomba, then okay, fine. Otherwise, okay. Very good.
This has different some feedback on the presentation.
No, I thought the presentation was very clear, but I thought the presentation was very clear. You had a good management of the blackboard, so I think that was good. But I think there were many points where your alarm was triggering. I'm not sure why they do this, I'm not sure why they do that. Be careful, your alarm needs to be sharper. You cannot, if your alarm rings, choose another paper.
Yeah, there was not like much time, but yes, I agree.
No, I mean, typically it's better to pick papers that have more citations. This one has like 15 citations, and most of them are self-citation. So you could think, is this really an important paper, or some curiosity, or yeah, if the paper has very few citations, it can mean that it's just a topic that is not a hot topic, and that's fine. Or it can mean that there are some things that are either not interesting or wrong, and we should be careful and check. Okay. But otherwise, I think it was nice to make contact with the lecture, to emphasize what's similar, what's different. That I thought was good. Yeah. Okay, so we'll describe this paper by Witten. It's a big paper, so I'll pick a few things and we'll see how it goes. And so where Witten tries to make precise some aspects of ADS-CFT. So this was right after Madsen had proposed ADS-CFT. So he had said that there is a duality between CFT and the theory of quantum gravity. And this theory of quantum gravity turns out to be type 2B string theory, which is approximately equal to some 10D supergravity theory in some approximation, where the key object is this anti-de Sitter space that we are going to discuss a lot. There's also some compact space, but the important part is ADS. So this is anti-de Sitter in 5 dimensions. And then the prototypical, this is one example of ADS-CFT. And the example of the CFT in this particular example is a theory known as n equals 4 super units. And that theory is a theory in d equals 4. So 4 is not 5, so it's one less dimension than 5. And it's a conformal full theory. So it's a theory with no scale, or with scale invariance. And Madsen had understood this by taking a setup in string theory, taking a low energy limit of some stack of d-branes, like some piece of material, a stack of d-branes, and Madsen said, let's look at this stack of d-branes and let's take a low energy limit where that low energy only massless modes interact, and that gives the CFT. But on the other hand, this system, I can also understand it as back reacting on the lab where the system is. So by taking this low energy limit, Madsen understood that there were two ways of describing it, either as string theory or as a CFT, and therefore he said, because of this, these guys must be the same. But said like this, it's very vague. I'm just telling you that two theories are the same, and this duality is kind of useless unless you have a dictionary between the two. Unless you tell me, okay, fine. So if I compute here on the CFT, for example, correlation function operator, so suppose I have an operator and I compute an operator at some position x1, another operator at some position x2, and so on, in the CFT. What is this equal to in the supergravity sign? What computation in quantum gravity should I do that gives me this? And similarly, if you give me another computation in supergravity, what is it in the CFT? And you need a map between the two. Okay? So the paper is about the dictionary. not about how to come up to the duality, but given some duality, you are given the duality. And the question is, how can we try to guess or come up with a dictionary of basically the only thing that could make sense? What could be correlation function in the CFT, what could be the quantity in gravity, and so on. So you can think that someone came and told you, oh, this for this CFT is equal to 5d quantum gravity, and then they left. And now you have no idea where this came from, and it just tells you this. Okay, you can do some computations to try to check, but to do that you need the dictionary, otherwise you can compute things on both sides. You get 0.76 on one side, here you have 3.2 on the other side, but now you need the dictionary. Maybe the prescription is divided by 4 and then okay, so good. Okay, so this paper is about establishing this dictionary. So we can discuss a bunch of things, and I'm going to cover maybe a few, I don't know which ones, but we'll see as we go. How much do people know about what is in this motivation part of the blackboard? For example, conformal field theories. Who knows about CFTs? Martin, a little bit? Not much. And who knows about ADL? What is under the Caesar space? More or less? A little bit? Okay. Anyway, so for some of you it will be probably a bit boring. I'm going to review some of these things, but it's good that many people already know it. Okay, so let's maybe recap a little bit how to think about ADS. So Witten points out that ADS, you can think of it as in embedding space, saying that I have a bunch of variables, uv minus a sum of x0 squared I always forget the signature. Make sure it's okay. X squared plus x squared plus x d squared equal. And then the first thing is that we can write two equations here, 1 and 0. And the claim is that this space with 0 describes in a way that we are going to explain flat space, and the one with 1 describes ADS. And by flat space, I mean flat space Minkowski 1, d minus. So this is a d-dimensional space, and this is a d plus 1 dimensional space. Okay? So let's see that first of all if it has any chance of being correct. So let's look at the first one, d plus 1 dimension. Is it possible? Let's see, how many variables do we have? We have d variable plus 2, so we have d plus 2 variables. But we have one condition, so it's d plus 1 dimension, right? Like a sphere. It's x1 squared plus x2 squared plus x3 squared, that's a two-dimensional sphere. What about this one, 0? Well, it's still the same counting of variables, so it's d plus 1 variable, so it cannot be a d-dimensional space, as it's written, right? So the way it works is that for flat space, so here, we say that these variables are identified up to rescalings. So u, v, and x's is identified with s times u, v, and x. Okay? So strictly speaking, what we have here is some projective coordinates. So the overall scaling of all of them doesn't matter. So I can set one of them to 1. And therefore I lose that variable and now the dimensions work. Okay, so that this describes flat space now is kind of clear because I can say that the flat space part is here. This has all the coordinates to describe the flat space that I want. Right? And then it's projected, so I set u to 1, for example. And then V6 means whatever this is. Right? So it's done. And then the claim is that this space describes ADS. So, by the way, it's also often convenient to write this guy, writing U equal to some X. Let's use some X that are not used there yet. So X minus 1 plus X, for example, D plus 1, and V equal to X minus 1 minus X D plus 1. So if you go to some kind of light coordinates like this, then you see that this whole thing becomes X A becomes just X A X B eta A B, where this eta as signature with signature it has it has signature, let's see, so 1 plus from here, so the first component minus 1 is plus, the next component 0 is also plus, then all these guys come minus, and the RD are done, and then the last one is also 1. Right? That's what this line becomes. And so, we can think that this space is embedded in Minkowski space, but a special Minkowski space that has 2 times, and this plus 1 space directions. And then with these 2 times, there is this embedding condition there. Okay. And now, okay. So let's try to draw this. Let's try to represent this space. For let's draw this in the simplest case, the one that we can draw. So let's draw ADS2 to understand what's going on. So in the case of ADS2, so that means D is equal to 1. I'm doing something wrong. Sorry, I'm doing something silly. Yeah, I'm doing something silly. So here it's D minus. This is D. Here it's D minus 1. Let's check that the dimensions are correct. So 1, 2, 3 plus this, D plus, yeah, that's it. D plus 2, 1 condition. Okay, and so here it's Minkowski 2 condition. Okay, so for D equals 1, we only have this condition here, and then we get the condition that x minus 1 squared plus x0 squared minus x1 squared equal to 1. And that describes an hyperboloid. So if we draw this, you see that it describes an hyperboloid. Let's draw it and see if you agree. So I want to claim that it describes something like this. Okay, some hyperboloid like this, where this axis, where there is a rotational symmetry here, so this axis is x minus 1 and x0, and this axis would be the other one, this x1 here. So that's clear, right? That the radius of this guy, this plus this square, is equal to 1 plus this guy. So the minimum is 1 here in the middle, and then it grows, and you get bigger and bigger circles as we go here. Okay. So this space is ADS. And on the other hand, in this space, 0 describes light rays, and so ADS. Now, if I draw the light rays that pass by the origin here, so this would be the light cones that pass by the origin. Okay. And so you see that we are saying that a point in Minkowski space is a point, is giving a light ray. This is the same as this, is the same as this. So giving a point with this identification is giving a light ray. So for example, you could give this light ray that goes to this point here. And you see that giving a light ray is equivalent to giving a point at the boundary of ADS. These two guys are close to each other. And so, indeed, we see that this yellow is the boundary of the white. Whereby the yellow, I mean the light rays. Because the light rays, each point, the y asymptotes to, as I go further and further away in the hyperboloid, I go to some point here. This point is associated to this light ray that goes to this point. And so on. So there is a map between boundary points, light rays, and boundary points of ADS. But each light ray defines uniquely a point in Minkowski, as we agreed. And so, the boundary of ADS is Minkowski space. Okay. So we see that this boundary of ADS at d plus 1 is Minkowski space 1, comma d. Another way of seeing is that when I go very, very far away from the boundary, I'm effectively dropping the 1. It's like when you have a massive particle and you boost it a lot, effectively it becomes massless. Right? In practice it moves at the speed of light and you can ignore the mass. Right? And that's what's happening. As I go to this hyperbola, I go very, very, very big, asymptotically I'm effectively null, and I can ignore the 1, and then I go from ADS to flat space by ignoring the 1 when I go very far away to infinity.
Good. So
Yeah.
Could you repeat the first argument on the identification of the light rays with the points of Minkowski? I don't think I followed it.
So I'm saying that this point is rescaled to this. So this point, I can always say that this is equal to u. I can always rescale it by x. X is a point of Minkowski. This is 1. This is some v that is uniquely fixed by x, because the condition that this is null fixes this guy unique. And this I don't care, because it's up to rescaling, and so, given any point x, I construct a light ray in this point. Right? So you give me a point in Minkowski, I complete this to make it null, that's a light ray. Conversely, if you give me a light ray, rescale so that the component is 1, and you get a point in Minkowski. And so the map is 1 to 1, there is a map between each point in Minkowski and a light ray in 2 dimensions higher. Now, look, this x minus 1 and this x 0, they were times. This was a time, this was a time. But you see that this surface here doesn't have 2 times the surface itself. It only has 1 time. And the time is actually this direction here going around. You see that that's clear that when I'm here, I'm moving in this direction, which is x0. And then I go here, and when I'm down, I'm moving in this direction, which is x minus 1. And later I'm there, and I'm moving in that direction, which is again x0. So as I move here in this single direction, I'm moving in either this x minus 1 or x0 or a combination of both. That's a time direction. But I don't move in this, or I don't leave the blackboard. So I don't explore the two times. I only explore a combination of the two. So there's only one time here. Right? So this direction going around like this symmetry that of this picture. This is one time. So ADS just has this one time here. Similarly, in the boundary, time is this circle here that goes around. Now, you could be a bit worried that if this is time, time is periodic. Right? And so that's true. And so what we have to do is we have to say that ADS is, we have to put some funny U here, to say it's the universal cover of this business. And by universal cover, we mean like toilet paper, that I go around, and when I come back, I'm on a different sheet. And then I go around, and I don't identify. I keep on going. I unwrap this hyperbola. And so I think that as I go around, then I'm on a different piece. And then I go around, and so on. And you see that I try to draw here a bunch of copies that I go around, and around, and around. You see? And so now, I unwrap, I just say that start with this space, and universal cover it. Then we go around and don't identify things. And that is a space that has one time, and it has no closed time-like curves, and it's well defined. And now, in this space-time, and that is what ADS is. Okay, good. So there is this statement that we have the theory with ADS. So this is where there is quantum gravity. And then the boundary of it is a field theory, and that is where there is a CFT. And so the proposal is that instead of describing things inside ADS, you can describe things in the boundary of ADS only using a CFT. So that's what ADS CFT tells us, that this is how things should work. Okay, very good. Any question here? Okay. Now, so next,
taking the universal and embedding the universal cover doesn't change the embedded space, right? So you can still argue that the boundary of the universal cover is still in the cost space.
that the boundary is still Minkowski space. Yes, the boundary Minkowski space, because before it was Minkowski space with identification.
Yes.
And so now we unwrapped it. So when we do the universal cover, before we did the universal cover, this space was topologically S1, this time circle, times S d plus 1. And because we did this universal cover, this S1 becomes I under the universal cover. And the boundary now, so the boundary of such space is as d plus 1, which is like Minkowski, but sorry, it's R times S. And I go very far away from the blue. Okay. Now, so this is how we see ADS from this embedding coordinate. And you see that this has a chance of being correct because a CIT has a group, a symmetry group which is SO2, comma D. And this space, by definition, is invariant under SO2, comma D because that's, by definition, the symmetry that preserves this metric. Okay, so next, we can say we don't need to study this Lorentzian case, we can study the Euclidean case, which is basically putting a plus sign here. And then we are describing now Euclidean ADS, which for most of the talk we'll just call ADS, as in the paper. But we have to keep in mind that that is the one where now we don't have the time. So if you think of it, the picture now is no longer this, instead of this hyperboloid, now you will have more like a parabola. Because you flip that sign under the space. And now, light rays are still the boundary for the same reason. They approach also the boundary of this space. And now there are two disconnected components, and we take this to be Euclidean ADS. Why are there two disconnected components? Because now you see that this quantity is positive. So you put it on the right hand side, you get 1 plus a positive quantity. So now, if UV is positive, it stays positive, it cannot pass by 0. Right? And if U and V are negative, they stay there, they cannot pass by 0. So there is this region where U and V are positive, and this region where U and V are negative, and they don't talk to each other, they don't pass by 0. Right? 0 is not possible now with that plus sign. So we have these two components. And that's how we think about this space. Now, you see that this space, basically, if you look at this, is like a ball. Right? So this is like a disk. And so this is, from a picture, if I see it from above, this is like a disk. Right? Where this is infinity and so on, but this is the topology of this. So this is this famous picture of Escher, where I have this disk, where they have the fishes that become smaller and smaller and smaller as I go to the bottom. Right? So that's this picture. Escher, I'm not going to draw with the fishes and so on. That's looking at this picture from above, where there is this space going further and further to infinity, so it's not common. And so, now, of course, when you write a space-time, it's very important to keep in mind that you can write many metrics, and you should not think that different metrics are different space-time or with different physics or anything. I mean, it is just, you choose whatever coordinates you want, and the physics is all the same, but some coordinates are nicer than others, and some coordinates highlight some symmetries, some coordinates like this make manifest the SO2, comma D, some coordinates make manifest that it's a disk with, where the metric blows up at infinity. It's up to you. So you can take this space, parameterize it in some nice coordinates to make this disk manifest, and you get this metric of Euclidean ADS, which is equation 2.1 in the paper, where the metric is just the following. So you have 4 times sum from I equals 0 up to D of dy squared. So you see it's the flat metric in D plus 1 dimensions. ADS is a D plus 1 dimensional space. But, as we say, this metric blows up when y goes to 1 squared. So this is just a nice choice of metric where we stay inside the coordinates of radius 1. The y's are just some coordinates in this disk. But as I go towards the boundary, the metric becomes very large. So that's exactly Escher's picture. So this is exactly what it is. So there is a very simple setup way of parameterizing these variables such that this is manifestly true, right? Such that this is trivially true, and when you get that, you get that picture, which is it also has other names like log chest space and stuff like this. You might have. Okay. And so we see that this absolute value of y is smaller than 1. And the boundary of this space corresponds to sending this y to 1. Going very far away to the boundary. Now, how do we go to the boundary? We cannot just go to the boundary. If I just go to the boundary, the metric explodes on my face, right? The metric is just exploding. So what can I do to go to the boundary? I can take my metric, ds squared, and say, define ds squared, try to find a way of going to the boundary. But I have ds squared, and as I go to the boundary, ds squared explodes. Okay, so if I take ds squared and multiply it by something, f squared, such that this becomes finite as y goes to 1. For example, you could take f to be just this factor here. But it's not unique. The choice is not unique. You can do one choice and you go to the boundary. For example, if you do this choice, then ds squared of the boundary is just flat space. It's just Rd. Right? Because you see, you take no, sorry. It's wrong what I wrote. What is ds squared of the boundary? You take out this factor, and then you go to the boundary where y is equal to 1. Right? So y is equal to 1. So I get the flat metric in d plus 1 dimensions with a condition that it's 1. So it's nothing but a sphere. Right? So in that case, the boundary, this boundary that I get, if I do this and then I go to y equal to 1, I get flat metric with y equal to 1, that's a sphere. But it was not unique. I have to do a sphere, but I can also multiply this by some other smooth function, lambda, and then it would be the metric of a sphere times lambda. And this is what's called a wild transformation. When you have a metric and you multiply by a point, by a local rescaling that depends on the point that you are on the space. So it's like a local dilatation of your space. So it looks like the boundary, you cannot really say what's the manifold. It's really the manifold of the wild transformations. I mean, it's up to you. You choose how you go to the boundary. And if you go in a certain way, you get a sphere. If you go in another way, you get a wild transformation of the sphere. And you have many ways of going to the boundary, of regulating how you go to y equal 1, and getting different spaces, different things that you would call boundary. And that's fine, because this, not getting a metric, not getting a space, but getting a conformal structure, is actually very friendly to a conformal field theory. Because a conformal field theory is a theory that says precisely that it's defined by saying that if you compute correlation functions in a given space, these are trivially related to correlation functions in another space that differs by local rescaling head, or however you want. And that's exactly what a wild transformation is. So the fact that we have this freedom of going to the boundary and getting different wild factors is not a bug, it's a feature. It's good that we have this freedom. Because in the CFT is very friendly to changing this wild factor. So indeed, I remind you that a way of defining the CFT is the following. If I have in a CFT some scalars, x1, etc., in the CFT with metric, with a given metric that is lambda of x times a metric G of space-time X, that this is trivially related to the correlation function of the operators O of X in the same CFT with metric G of X. That's the definition of CFT. Except that they are not exactly equal, but the prescription is that if you restate, you pay some factors, lambda of x1 to the power delta 1, lambda of operator x2 to the power delta 2, etc. So if you tell me I have a space-time which is, say, flat, and now I will apply a transformation that will contract space here, apply a dilatation there, do nothing there, and so on. And I have a bunch of points, right? So that action of doing this dilatation, I can totally ignore it, and that's the same as before, up to some trivial factors that locally just depend on what dilatation did you do at point x1, what about point x2, what about point x3. So up to some trivial factor here, that's what we do.
I always forget this. Do you just need the Weil factors even when the operators have spin? Or?
No, this is for a scale of operators. Okay? So we have this definition, if you want, of if you are in a CFT, then this very powerful symmetry of correlation function. See that if lambda is constant, it just tells you that if you make a dilatation of all the fields, you pay factors of lambda to the power deltas. Deltas are called the dimensions of the fields. So that's a more standard thing, that if I have fields not in a CFT, but in a theory where they have some dimension, then if they have some mass dimension, when I dilate things, if I dilate everything, I pay some overall factor that is dimensional analysis. What is non-trivial is that here we are allowed to do not just global rotations or dilatations of everyone, but we are allowed to do dilatations locally. Which, if you want, is very physical, right? If you tell me that I have a symmetry that at some phase transition I can zoom in and out arbitrarily, then you say, okay, but I should be able to do it by different amounts in different regions. Why would I have to do the same zoom-in transformation, right? And so it's only natural, and indeed that's the definition of a CFT. And we see that, so it's good to have a framework where the metric of the boundary I can easily change if I want. And that's exactly what we get. So when we have these boundaries where things blow up, we go to the boundary by approaching it in a way that is up to us, and that should give us some freedom. Good. So, since we are here, let's do an application of this formula to get a bit familiar with this formula. And let's suppose that I want to use this formula to learn about what is the correlation function of putting a scalar at position x, and then at position x1, and the scalar at position x2. Right. So, what is this? Well, and the claim is the following. So, you are putting your say, one position, one point is x1, one point is x2. And I say, think of this as this point being 0, this point being 1. But if here you add some metric g, now here you have a metric where this distance 1 should be g times the distance between x1 minus x2, where this is a constant. So I rescale the metric by a constant. This is the same. No one can tell the difference, right? It's like just saying I have 12 centimeters, or I have my favorite unit, 1 billion. 1 billion is 12 centimeters. Okay, fine. I just rescale things and choose a different metric. Right? It's absolutely equivalent. So these points at x1 and x2, it's the same as thinking the points are just at 0 and 1. But the metric now is not this metric, but it's the metric rescaled by this. So that when I compute the physical distance, it's the same thing. Okay, but then I wanted to compute my correlation function of x1 and x2 in my original metric. And the prescription is compute it in the new metric at position 0 and 1. Right? Well, at position 0 and 1, the correlation function is just some number. It doesn't depend on the positions because it's at position 0 and 1. These here depend on the position. And so this factor here, when I divide on the other side, I conclude that this correlation function is equal to this number. The number is just a correlation function when one is at 0, the other is at 1, divided by these factors here. The two operators have the same dimension delta. The rescaling was by x1 minus x2, so I get x1 minus x2 to the power 2. And so I conclude that in a conformal field theory, correlation functions of two scalars are power law. It's a number that I don't care, that's just normalization, I can absorb it. But the space-time dependence is just x1 minus x2 to the power 2. It's actually quite powerful, this way of thinking, because you can actually use this to derive right away without any work the 3-point function. Because you can say a 3-point function of points at arbitrary positions, I can rethink of it as some fixed positions with a funny metric. That's possible to do, it's easy to do. And in this way, all we have to say is that then that stuff at fixed position is just a number, and I just need to work out the transformation to that new metric, and I read off the space-time dependence of the 3-point function, and I will tell you what it is. For the 4-point function, this trick no longer works, and the function can be more complicated. And so in the CFT, we have this set of numbers. They are called the dimensions of the operators. And then correlations, and then these numbers are very important because, for example, the 2-point function of operators are governed by the dimensions of the operators. So knowing the dimensions, like knowing the critical exponents of the theory, tells you how all correlation functions decay with power laws, what are the various power laws that appear. Okay. And so an obvious question we would like to address is, there are 2 questions we would like to address. One question you could ask is, I have correlation functions O of x1, O of x2, etc. in the CFT. What is this equal in gravity? How would I compute these correlation functions? They are given, of course, in the CFT by definition. They are given by the path integral over all my fields, exponential of the action of my fields, and then operator O at position x1, etc. Right? That's the definition in the path integral. What should I do in gravity to compute this correlation function? Okay, that's a question. I would like to ask, what would it be? Maybe another question we could ask is, forget about correlation function, but you tell me that this set of deltas are important. They are nice numbers for different CFTs have different sets of deltas. So this is called the spectrum of the CFT. The set of numbers that give the various power laws of the CFT. What is this equal to in gravity? If I have a theory of quantum gravity, how do I compute these deltas? Or or said differently, if you tell me that this CFT is computing something contemporarily, what is that something that the CFT is computing by giving you the dot? Okay. And the third question we are going to address is that in quantum gravity, we integrate over spacetimes. And so, we can ask, do we really fix ADS? It's a bit weird. We should be integrating over spacetime. We should not be fixing a spacetime. So can it be that we should do something a little bit better than fixing ADS? And the answer is yes. And what we will see is that we should think of spacetime that are asymptotically like ADS. But inside they could be something else. Okay, so these are the three main things that this paper addresses. And so let's try to cover stuff. Okay. Yes.
So just a question. So that form of the 2-point function, the SFT, only depends on that normalization constant that we don't really care about in the spectrum of the operators, right? So if I give you a set of numbers and I call that the spectrum for some CFT, does that define uniquely a consistent CFT?
No.
At least the 2-point functions for
yes.
the CFT.
The 2-point functions, yes.
And the 3-point functions, because I think they also go with the initial.
No, the 3-point functions, no. So you can absorb this n, the normalization of the operators.
Mm-hmm.
When you do it, the 3-point function comes with a new number, and now that number is physical.
Oh.
So the 3-point function, there is one more piece of data: the dimensions and the number up there, which is called the structure constant. Precisely because it's like a structure constant. I have 3 operators, so it's like an algebra. These 2 operators, how they combine with the third one.
So if then I give the spectrum and those structure constants, then you can define the whole CFT by using
yes.
LPs, right? For instance,
then that would be the definition.
Okay.
But if you give me a spectrum and a set of 3-point functions that you dreamed of, that will not be a consistent CFT. So if it's a good set of numbers, great, that's enough. But most set of numbers are not good.
What defines a good set of numbers then?
For example, they will give you some OP, as you said, some algebra, 3-point functions. But that algebra you want it to be associative, you want it to be a good algebra. Right? So, but most numbers are not. Right? So it's like saying, here are the structure constants of my group, and then you check Jacobi identity and it's not true. And you say, oops. That is not good. The same thing. Okay. So this is one set of coordinates that are quite useful just to visualize this Escher disk. There are other coordinates that you can use. Let's just write it down. A few other examples of Euclidean ADS. Another way of writing Euclidean ADS is that dy squared plus sinh square of y d omega squared, where this is the metric of an SD, a unit SD. And now, again, you see that if you tell me that here we saw that in 1, let's compare 1 with 2. So 1 at absolute value of y equals, say, 1 minus epsilon. We got that the metric, if I go to this value, is equal to something times the metric of an SD. in 2, if I go to y equal to some big number, some big constant number, then I see that I go to a big constant number, and I see that my metric is equal to some exponential of some big number times this metric of NSE. Right? I just go to some big numbers. Okay, so in this case, we'll see the same thing. Okay, another way of representing yet this space is in the following way, where we, and this is perhaps the most famous way, we divide by x0 squared, and then we have sum I equals 0 to d dx squared. So that would be a third representation. And in this third representation, if you go to the boundary to some x0 equal to some epsilon, right, where the metric will blow up, then ds squared would be dx0 squared plus dx1 squared plus dx squared, which does not look exactly like SD. It looks like the metric of RD, okay? Which this looks just like RD, but actually RD is just SD if you add a point at infinity. And so it's the same thing, because the point at infinity is contained in the space-time. This is just the point x0 equal to infinity.
I think it would be dx1 squared plus, not dx0 squared. First one.
Sorry? So what you will get is you will get RD
Yes.
plus the point x0 equal to 0. That is plus the point x0 equal to infinity. At the boundary, that's also a point at the boundary. And the two combined is what gives you a sphere result. Apologies. It's just saying that infinity is just a point that closes it into a sphere.
He was just saying that this metric goes from 0 to d, so that's not RT.
Yeah, that's RD plus 1.
Sorry?
Which row is RD plus 1, not RD? So it's going from 0 to d. So that's
Yeah. That's not 0. I go to x0 equal epsilon, so I get a constant, which is just 1 over epsilon squared times. X0 is very simple. So let's just draw a couple of pictures. So this picture is the picture for 1. It's just the disk. This picture was the picture for the representation in embedding. Let's call it 0. That was the embedding one. What would you draw for 2? For 2, you would have that. For 2, you would say it's a cylinder. So there is a direction. There is an Euclidean time here. No, sorry, I'm saying something silly, right? Yes, I am. No, yeah, sorry, it's silly. Yeah, no. This is just, I would use the same picture for 2, where I will just say, I have a variable y here. This is just y equal infinity instead of y equal 1, but it's the same thing. And for that picture 3, then we say that ADS is a bunch of copies of X0. So we think of it as foliation, so many copies of X0. I'm drawing them smaller and smaller because you see that it's copies of Minkowski multiplied by 1 over X0 squared, so it's like smaller and smaller copies of Minkowski space. And as I said, this boundary, it's this space here, which looks like flat space, plus the point at infinity, and together it's the same topology as just the sphere. Okay. So yeah, so 2 points here are just 2 points here at the boundary. And there's just 1 point at the boundary that naively you don't see here because that is mapped to the point at infinity. Right? If you work out the map from one to the other. Okay? Okay. So now, so now the question is, how do we find the prescription for studying correlation functions in these spacetimes in ADS? By doing quantum gravity inside this spacetime. How do we do quantum gravity inside the spacetime to learn about correlation functions in the boundary of spacetime? Right? So the idea is that the CFT lies at the boundary of the spacetime. So the arrow is where the CFT is, and I have correlation functions in the CFT. Should be dual to some path integral inside in the full region, including the boundary and the bulk of gravity. Okay, so the first thing Witten starts analyzing is starting with a massless. Think of a massless scalar in ADS. So we are going to compute a massless scalar in ADS and try to see how that computation of that massless scalar could be related to correlation functions of scalars in a CFT. Okay, so we have a massless scalar in ADS, so it solves the equation equal to 0, where this is the Laplace operator in ADS, so the curved space Laplace equation. So okay. Good. So now there is the following claim, important claim here. That reminds a little bit our very first lecture, if you remember, which is the following. Suppose I have my boundary, and here at the boundary of ADS, my field phi is equal to some phi 0, where x is a point in the boundary. Alright, so I have some profile of my field here. So at the boundary, my field, I don't know, it's 0 with some bumps, I don't know. It's something like that. There is some profile for my field at the boundary of my spacetime. And then, so let this be true. Then the claim is that phi is unique inside. So given some phi outside, I can analytically continue and get a unique phi inside that and that goes to this, and that is a good solution inside. Okay. So that's a claim. The idea of showing this is very similar to what we did in the first lecture, when we showed, if you remember, that we had some Laplace equation and that solutions were unique, and you need to change a bit one solution, you needed to change another. And so how do we check it? How do we show that it's unique? So, well, because you can construct, imagine you had two solutions, and you could construct phi 1 minus phi 2, and you would call this phi. And then, by definition, as in the lecture, we would say that 0 is equal